Dynamic programming.
Dynamic programming is quite similar to divide and conquer, except for that divide and conquer doesn't store the values as it, so you can be redoing the same thing over and over and over again. An example of that would be, if you guys remember this table from the Fibonacci, where we calculated all these values, just as we're going down this path, we can say that, okay, we're gonna go for all the left-hand items first, start processing all these guys, and then all these, so, you know, we'll be done with this and putting the value here, and then done with this, and then keeping the value, so when we have all these together, then we keep storing the computed value. So what would be really useful in a dynamic programming algorithm is that by the time that we go on the other side, where we already have the 4 calculated, this tree and this tree are exactly the same. Essentially, it's cutting out extra work. In other words, by the time that you are going down the tree and then saying, okay, I'm going to calculate this guy, I'm done, I'm gonna then calculate these 2 and go back up, and then calculate this 2 and go back up. By the time that it goes to this 2, this tree is exactly the same as this guy here. So whatever result that you get from this would be applied directly into the algorithm. Then by the time that you get into calculating all these 3, when you get to this 4, the tree is identical to that, so you would just grab the computed value without having to go and calculating each one of these items under it. It will just grab whatever the parameter and value actually generated. So it's actually quite cool and quite interesting, because it saves a lot of problems by trying to optimize things that have many solutions, many of those problems. Finding an optimal solution for dynamic programming is actually important. So the steps for working with a dynamic programming algorithm, we're going to characterize the structure of an optimal solution. Then we're going to recursively define the values of such optimal solution, then compute the values of that solution in a bottom-up fashion, just like we did with the Fibonacci, and then we're going to construct the optimal solution for the information. Meaning that as we're going down the tree and then we're going back in our tree of results, you will already have those values pre-calculated. So when does it make sense to use dynamic programming algorithms? When something involves making a choice, where, for example, 2 + 2 = 4, there's no choice there. But there are certain algorithms that would require that you make an optimal solution. So when you have to have a problem that might have an optimal solution and you need to make a decision, that may not be the right and only solution, it's just a decision, a choice, being optimal is good enough. So the idea is to subdivide the problems into smaller things, into smaller chunks, so that way we have a cut and paste solution of the problem. And a good example of that, if you think about it, is just finding the shortest path towards a destination. We are trying to calculate the shortest distance between UCLA and the Santa Monica Airport. The shortest path between 2 points is a straight line. So let's assume that if we're going to calculate this, then we can start breaking it down into further sub-problems and apply it recursively. So we can essentially calculate the distance between this point, these little squares, that correspond to the bigger calculation. So we can figure out the distance between these 2 lines, the distance between these 2 lines, the distance between these 2 lines, and figure out what streets correspond in that situation. We can calculate from here to here, from here to here, and then when we have to make a decision or figure out what is best for our line, because our rectangle looked like this, so we have this path, or we have this other path, or we have this other path, And you can see how I'm going back again to the beginning and trying to like figure out what is the shortest distance. Like I'm going back in and then tracing it down to whatever I can get, like this, and trying to like maybe like this, maybe like this, and here. But every time that I'm going back, I already have some of the values that I've determined that are the smallest in a region. Like for example, this guy here, I already pre-calculated that. So I don't need to go back in and recalculate it every time. I can just grab a next starting point and then figure out in a smaller area how to get as close as possible to this tangent, and then compute the values. And then whenever I am done with the entire algorithm that goes all the way back to our Santa Monica airport, then we have a resolved problem without having to recalculate what is the distance between each one of those streets. And it was figured out in a recursive manner.
Greedy algorithm.
There's one extra concept I'd like to touch on, and that concept is what it's known as greedy algorithms. And a greedy algorithm is an algorithm that tries to choose the current best outcome by making a decision that what it thinks is the best decision. So for example, if I want to calculate not only the shortest distance but the fastest distance given traffic, and right now I am simulating in Google Maps the traffic on a Friday at 4 p.m., which is already a nightmare according to the 405 and everything else. If I want to drive from the Santa Monica airport and try to get to UCLA, how would I do that? Well, a greedy algorithm, it's going to take a look at traffic conditions and distance, and then probably choose, given the distance and the traffic, it might go for an unconventional route of something like this and then take you all the way down here, because it is what calculated that maybe traveling you a farther distance would actually get you there fastest. In an ideal no traffic situation, it's the exact same as what we have thought that it would be the shortest distance, or it would even prefer freeways. But with all those variables, meaning the volume of cars that can be transported, how dense they are right now, and the distance, seems that and the distance and traffic, well, and traffic is a variable that changes, that a greedy algorithm would be perfect for trying to determine the best way to get to a destination.
Amortized Analysis.
Let's talk about now amortized analysis. Amortized analysis is just a different way of calculating the cost of operations, especially useful when only one of the operations or a few of the operations is really slow and everything else is like really fast. A good example would be when we are sorting numbers, say from like a million numbers, and we're trying to make them unique, and we are leveraging the uniqueness of a dictionary or hash map, and we want to save it to a file. Typically, in that case, the slowest operation will be the saving of the file. Amortized analysis allows us to just calculate like the entire operation of that as the average of the analysis. So it's just a way of like calculating things in a different way. So there's three ways. The aggregate analysis, which is just the basic average. The accounting method, which basically once something exceeds the cost, we can assign a credit that it is helped by other operations to pay for it by operations that have a lesser cost. And the potential is backwards. It's essentially using to prepay. So prepay versus credit, tomato versus tomato.
Multithreaded algorithm.
Another concept is multi-threaded algorithms. And when we are analyzing multi-threading algorithms, we're not really worrying about like all the setup, communication,
load balancing, memory sharing, all those resources. What we are concerned more about is the processes that are spawned and in sync to try to finish some work. Basically, the way that we measure it is the total work of one thread divided by the amount of processes or threads. That's going to be what the analysis is going to yield.
Linear programming.
Linear programming was developed in Russia during World War II to try to maximize the outputs of problems that can be represented in a linear way. And what does that mean? So there are certain problems that you might have certain constraints. Like in this case, I am listing a product A, that costs $150 to be created, and it's sold at $195, and it takes 0.5 cubic meters out of a 21 cubic meter warehouse. Given a budget of $1,800 per month, and also that product B, for example, we have a business that is trying to make two products, A and B, and they only have $1,800 per month and 21 cubic meters on a warehouse. Product A costs $150 to make, and it makes $195 per unit, and it takes a small amount of space. Product B costs $100 and gets $150 for every ton and makes 1.5 cubic meters. And the reason you might be wondering, well, this one is a little easier because product A occupies less space. However, product B is easier to sell than product A. So, given all those constraints, when you chart them, you're basically creating a polygon. And there is an algorithm called the simplex method that keeps pushing the boundaries of all those algorithms, of all those parallelograms, to try to determine which one is the maximum that it can create, and that would maximize the gains. Approximation algorithms is just something that it's really useful for mathematical problems. And the technique doesn't really guarantee the best solution, as we have seen in some others that it's actually sometimes the case, but it's as close as possible to optimum. And a good example is the approximations of pi or even delivery routes.